Okay, so I hope every one of you revised the last to last lecture. So please give me a thumbs up if okay, anyway, any doubt in the last lecture before in the last to last lecture on the EM algorithm before we continue with it. And if no one asks anything, then I'll ask you all some questions. So please uh, just unmute yourself and ask if you have any doubts. Okay, I see there is none. So I'll just go ahead and ask you some questions. Okay, so first of all, what are we trying to achieve in EM algorithm? What is our purpose? It's a simple question. Can anyone answer that?
I can give a go.
Yeah.
So basically, we are using EM algorithm to train a latent variable model, and we apply to a number of different application. Like we can apply EM algorithm to Gaussian mixture model, or we can apply it to k-means. So basically, when we apply into Gaussian mixture model, we trying to like obtain the basically we're trying to do soft clustering to try to figure out which data point belong to which cluster, but rather than having a like a concrete value that okay, this data point belong to this cluster, we get a probability distribution where it says this is the probability of which cluster it's belong to. So EM algorithm is a very generic algorithm where it has two steps. So one, we have got E step, and then we got N step. So in each step, we try to maximize Q, and Q is it's a probability distribution that we have introduced when we have introduced the evidence lower bound. And then in M step, we try to maximize theta, and we keep the Q constant, and we keep doing this iteratively until we reach the until it converge. So if we apply this EM algorithm to Gaussian mixture model, then we would be trying to, so in that case, our theta would be the covariance matrix and the mean vector, and that theta would depend based on the applications.
Perfect. That's a good sum. Yeah.
Yeah, and also I think also another thing that we covered was that evidence lower bound. So rather than just introducing one lower bound, we introduced a family of lower bound. And what we did to do that is we used this LQ theta. And I remember, I think at one point you divided and multiplied by Q in order to introduce that, that probability distribution. And then we solve that equation to get to this equation here where it says elbow.
Perfect. Awesome. That's a good summary of the entire lecture. So yeah, we multiplied and divided by this distribution Q, and then we applied Jensen's inequality, and using that we got our lower bound. Yeah, so any doubts in that? And yeah, and then we also yeah, we showed why so yeah, okay, L we know is evidence lower bound. So another follow-up question would be, it is the lower bound to which quantity?
So it is a lower bound to this one, Px. So it's marginal likelihood.
Yeah, log of Px, but yeah.
Oh yes, yeah, log of Px.
Okay, perfect.
So we take the marginal likelihood, which is evidence, isn't it?
Yeah, correct.
Okay, got it.
And so we also showed that log of Px equates to this quantity right here, and then this Ki. So yeah, we also covered this alternate proof by so one is one comes using Jensen's inequality, and other comes using just adding up LQ theta and KL divergence. We get this log of Px term. So we know KL divergence is always positive, and hence the lower bound that we introduce is always the evidence lower bound, variation lower bound is always less than equal to log of px, which you wanted. So we'll use this equation. So I hope you don't have any doubt in this equation. And also the this, yeah, the entire EM algorithm revolves around these key steps. And of course, the definition of the lower bound. And yeah, remember, so this is assuming that it's a discrete distribution. That's why Q of Ti is equals to C. This comes out to, it's a summation, but if it's a continuous distribution, then we would replace the summation with integration sign. So in the continuous case, it would be Q log of that term. Yeah. So yeah, I hope there are no doubts in this. So I'll be continuing further. If you have any doubts, please go ahead and mute yourself and you can just ask me. So with that, we'll start today's session. I'll just write down the stuff that I previously mentioned once again here. Log of px. So I'll just reiterate the previous things. And here, remember, in the E step, we consider theta is constant. In the M step, remember, we consider distribution Q is constant. So we'll start with solving the E step. Just plug in the equation of this. So, and we know L of theta Q. So the lower bound is just, this is a summation over samples. And in discrete case, this is a summation over all the classes. Yeah. So we'll just plug it in the Argmax and see how it evaluates. So first of all, just remember your Q. This Q is a distribution. So it's so maximizing over an equation, but in the functional space, as I if you recall earlier, I had mentioned that it's a difficult thing for us to do, right? Because all we have all we have learned yet so far is just functional normal variable calculus, where all we optimize is over fixed variables or parameters, but we don't know how to optimize over the function. So like in this, our goal is to search in the functional space, and so the mathematics that deals with this is functional calculus. So and yeah, so I have never learned functional calculus. So how changing a function changes our original equation of it. So luckily we don't need to dive into that, because as we know, so from this equation we can write, so first each step, we can write LQ theta as log of px minus scale divergence of this term. And what we are doing is we need to do maximize over L of Q theta. So our goal is maximize over theta log px. Now we know this px term is completely independent of theta. So yeah, we can just ignore that. Oh, sorry, this should be maximize over the distribution Q. Yeah, this each step, in each step we are trying to find the distribution that gives us this, that maximizes our lower bound. So yeah, this log px term is completely independent, so we can ignore it. And then this becomes argument Q. Okay, a question. What is the minimum value of KL divergence?
It's always
If it's
greater than
like-
equal to 0.
Yep.
It
Yeah.
should be 0.
And when does it equal to 0?
When
both
P and
distributions
Q
are
is
same.
equal.
Perfect. Awesome. So so see, like this is a key step, like where we avoid doing all the functional calculus and all those messy things, because we know the minimum value of KL divergence always equals to 0, and that's always when Q is equals to P. So the solution of this comes out to be yeah, so setting Q is equals to, okay, and yeah, what is P here?
What
So,
is it again?
yeah, so like this P, if you remember, what yeah, so like this is a shorthand notation. What does P represent here?
Isn't that the probability of the marginal likelihood?
It's
No, no.
posterior distribution condition on latent variable, right? Latent space.
Yeah, so perfect. So if you, in my review 4, when we did this, so here P was defined as here, this probability of the latent variable, posterior on the latent variable given your data point, your z given x. So even if I shall go through the proof once again, so if you see, we marginalized out. Yeah, sorry, go ahead. Okay, so we marginalize. Yeah, sorry, say. Okay, so we marginalized out our latent variable z, and then and this is the definition of lower bound. So as I mentioned, we are using P and Z interchangeably, but in this proof from Bishop, so to keep the notation consistent here, Z is the latent variable. And this is a definition of a lower bound. And this in the scale divergence, we define P as the posterior of z given x, and z is a latent variable. And if we just add both of these terms, the lower bound and the KL divergence, the q of z terms comes common. Then we apply the logarithmic rule, and x joint probability of x comma z, we write it as z given x times probability of x, and everything, q of z cancels out, z given x cancels out, and then we are left with this term. And then log p of x is independent of the latent variable z, so that comes out. And then this term, because we assume z is a discrete distribution, otherwise it would have been an integral sign here if z was a discrete. Sorry, if z, we assume z is a discrete distribution, otherwise if z was continuous, it would have been integral sign. But anyway, this term would come out to be 1, and then that's why it just disappears, and then we are left with log px, and from there we have this equation. But in this, we started out with assuming p is a posterior of z given x. So I hope that's clear. I hope you have no doubts on this. And hence, in the E step, all we need to do, so like solving this equation leads to the solution that q of k plus 1 leads to p of z given x. And so this is for just to keep the notation consistent, I will replace it to this. So for every for every variable xi, we have this ti associated with it. So and so we know q is a distribution on the latent variable, right? So with the notation of ti, so the E step basically simply comes out to be this: for every xi, we have a ti, and then for that ti, we write it in the E step. All we do is equate it to the posterior. So in order to obtain this, with this, we get the KL divergence goes to 0, and then LQ theta directly equates to log of px. So, any doubts in the E step? All you need to do for the E step is to get the posterior. Okay. So, yeah.
Like I had one doubt in this case. Here it's like basically, so we are basically using the same data, but we are getting some different distribution based on like the model parameter theta, right? Like that was constant, right?
Yep.
Or like are we basically using sort of a batch of data, basically, or the entire data?
Yeah, so you are using your entire data, but you have restricted yourself by some parameter, and that's the theta. So if we had the most optimal parameter, then our problem was directly solved, because with that parameter setting, so basically as I said, we have these two knobs. One knob is of distribution q, and other knob is of parameters theta, and we are trying to find the optimal settings of both these knobs to make our lower bound as close to log p of x as possible. So we keep in the E step, we keep the theta knob as constant, and we are rotating this q knob and trying out different distributions. And then for this particular value of theta, what we did is obtained so for that particular setting of theta, what we did is made RL of q theta as close as to log p of x as possible. But we are using all the entire data. Yeah. So in the diagram that I showed you earlier, it's something like, so let's say this is your log p of x. this is your theta. So what's happening here is we have chose this, let's say this is some theta is equals to theta k, some constant value. And in the first iteration, we would just choose theta randomly. And so we have this line. And with this, we tried a bunch of different lower bounds. So all of these are distributions, and see that I'm always ensuring this blue curve is always below the black curve because it's a lower bound. And out of all of these curves, we need to choose that, so we need to choose our curve in such a way that that's maximum at that particular theta. So our curve would be something like this. This would be our curve. Because here at this point, both these quantities are equal, log p of x. But see, only at this particular value of theta. So currently we have this as a Q distribution. And now we cannot go further than this because it's for this particular value of theta, it's restricted, this lower bound is always less than log p of x. And
your voice is breaking off for me. Your voice is breaking.
Oh, sorry.
Seems fine for me at least.
Okay. Nice. I'll repeat what I said. So we know this log. So we know this lower bound is always less than log p of x, and we are trying in the E step, we are trying to increase it. So but since it's always a lower bound, all you can do is just equate it to log p of x, and it cannot increase further because it's bounded by log likelihood. So that's why, and that's exactly because we equated this term to 0. We chose our q as the posterior, so this term became 0, and then this is a maximum we can increase of LQ of our log likelihood. And but that's for this particular value of theta. And so in the M step, and then in the M step, we'll also try to change this theta as well, so that we can get a better estimate. So the summary being that in the E step, all we need to do is equate our distribution, variational lower bound, variational distribution Q to the posterior distribution. And this is a very, in some cases, this might be a very hard thing to do. So in the discrete case, it's sometimes easier because it's easier to, so you need to evaluate this, right? So as I said, if you remember in the latent variable, when we're talking about latent variables, we generally have the information about how our data point. So this is something we model. How, like, given the latent variable, how our data point came out to be. So this is a modeling assumption, and the distribution of our latent variables. So we generally have these two quantities with us, but in this we are interested in finding the posterior. So you can simply apply the Bayes rule here. And then what we can do is marginalize out again T. So solving this is sometimes gets pretty hard. So when does it get pretty hard? So first of all, if let's say, so if it's relatively easy when t is a discrete variable, because then this you can just replace this integral sign with summation sign. So and in GMM we'll see exactly doing this, where we'll assume that ti is a discrete variable. So but if ti is a continuous variable, then again, as I mentioned before, you run into this problems of like this, that it just looks simply a single integral, but it's a sneaky integral where you have, like, if t is a 10-dimensional variable, then there are 10 different integrals lined up together. And yeah, so in GMM, ti is discrete, so it's easy. Then in probabilistic PCA, we assume ti is a normal. Ti is continuous. So this is not an assumption, sorry. Ti is continuous, but we assume ti is distributed normally. So we have probability of xi given ti is normal, and probability of ti is also normal. And if you remember from the last lecture, what we were discussing is for normal distribution, many of the operations that you do on normal distribution, it comes out to be a closed form. So you can avoid doing all of those integrals and directly get a closed form solution for p of x. So even though ti is some n-dimensional variable, you don't need to do n different line integrals. This thing, you can directly get a closed form solution for this. So this tied into our last lecture when we were doing operations on normal. But so yeah, when ti is discrete and when we assume that probability of ti is a normal distribution, our job gets easier. But that's not always the case. And that's why there are this different modeling assumptions. So one is this mean field approximation, and that's what used in this LDA. So in latent Dirichlet model, what we assume is ti follows a Dirichlet distribution. And so yeah, again, so ti is a continuous random variable, and ti follows a Dirichlet distribution. So all of these cannot be assumed. So in order to solve all of these, there is this mean field approximation. It comes under variational inference. So because it's not always easier for us to calculate the posterior, and the mean field approximation is approximation like it's kind of a factorized distribution. What it assumes is, so I won't go into the depth of it right now, but this is kind of what it assumes. So you cannot, because it's difficult for you to calculate the posterior directly. So you kind of make such an approximation, and then you won't be able to equate q of ti to this directly, because now what you're doing is you are restricting your functional space. So now you are putting some restrictions on q of ti. So this factorized distribution says that the restriction should be that it should follow this. And so now you are in this restricted space, you are making it as close as p to the possible, as close as, yeah. So the scale divergence term doesn't go out directly to the zero, but it's as small as possible. So we'll talk about it if we have more time in the future, but yeah, just wanted to let you know. So this, like, people talk about mean field approximation, and it tries to solve this problem of in the E step when we equate the posterior to the variational distribution Q. So any doubt in the E step, but for GMM, all we need is just this equation. Just, yeah. Solving the E step, if we had all the resources in the world and if we're omniscient, then this is what we would have done. Just equated Q to the posterior distribution. So Any doubts in the e-step? And I hope my voice was clear and you got it. So I think we are fine with e-step. Yeah.
Finally, like, can you explain a bit about like how mean field approximation kind of like uh, breaks this particular probability value into like sort of individual probabilities of the distribution? Like,
No, so
is it
this is the approximation. So it doesn't break. So it's like,
so
yeah,
it is kind of in a way similar to independence, right? In some sense, like it assumes
yeah,
that
yeah.
the distributions are like independent in a way, like they do not like modify the other distributions sort of.
Yep. So
Something like that.
yeah, exactly. It's an independence assumption. So it's exactly that. So it's like all. So if you have this and these T1. So I think this is a mistake notation. Notation on my part. So this Ti is when I write Ti, it means that the latent variable associated with ith data point, but this T1, T2 are the this T1, T2 are not the first data point, second data point, it's a dimension. So like all the problem arrives because in most of the cases we wouldn't be dealing with some single dimensional latent variable, uh, because if it was single dimensional, then there is a pretty high chance we'll be able to solve this integral. But it's generally we have this n dimensional, yeah, n dimensional latent variable, and these are those those n different dimension of a single latent variable. So T1, like if Ti would be Ti1, Ti2, and these are just n different dimensions. And what we are assuming in mean field approximation is all of these are independent of each other. And this assumption is nowhere warranted. It restricts our capability by with lot, and that's why the KL divergence term can no longer come out to be zero, because in this what we need is Q needs to be free to go anywhere in the space. So if so if this is P, and when I say P, I mean the posterior. So you would see this diagram coming up a lot, even in the lectures. But now what we were trying to do initially is we had this whole of free space and we were just equating Q. So to P, but now we are restricted by this boundary. And this boundary is defined by our factorized approximation or mean field approximation. And we can try to bring as close as possible. And so that's why we would end up at this. So there will always be still this much difference. But it makes our calculations tractable because the posterior is impossible for us to calculate in such cases. So that's why, so because we cannot calculate this, we bring it Q as close much as possible to the P. But you are right, this is exactly similar to assuming all the dimensions are independent. And how it simplifies why this thing is why we are able to calculate this thing and not this thing. It's a deeper topic, and then if time permits, I'll do it in some of the later lectures. It's an entire lecture on its own. But so I just wanted to know like where mean field approximation comes into picture, and this is where it does. In solving the e-step, and this posterior is not tractable. But in GMM and even in probabilistic PCA, this thing comes out to be tractable because we are dealing with normals or discrete variables, and for discrete, this thing boils out to a summation sign. Yeah, good question. Any further doubts? And I know this is a hard topic, and even in my university, this is taught in some upper level graduate class. So yeah, please don't feel bogged down by all of this. And if it's difficult to grasp, even it took me months to understand all of this. So please just say if you have any doubts. Yeah, I will be happy to clear those.
I've,
And yeah,
oh, sorry. Yeah. If you scroll up, the diagram. So we basically need to maximize our marginal likelihood, isn't it? Which you have written as P of X.
So we are maximizing over this. So maximize. I didn't get the question exactly.
So we're trying to maximize the log of P of X, which is our marginal marginal likelihood.
So that's the goal of this entire EM algorithm. What like the entire goal is just to find a set of parameters theta. So this P of X is governed by this parameters theta, and the entire goal of this is to find those particular settings of those parameters, find those particular setting of parameter that maximizes a likelihood, yeah, P of X. And then, as we said, maximizing P of X is same as maximizing log of P of X and all of that. And so, and in this we stopped at this particular value of theta, but yeah, so basically it's like in the E step, we are not getting any information. We are just getting, so E step is kind of an intermediary step where we have obtained this distribution of optimal value of distribution Q. But what we are interested in finally, after the entire EM algorithm terminates, we need this golden setting of our parameters theta that gives us maximum value of log P of X. So like in an ideal world, this theta setting is something that we would want.
Right, yeah, and the reason we're maximizing, like we find a lower bound because it's difficult to like directly maximize this log P of X, right?
Yeah, correct.
And why it's difficult to find? Because like, for example, in previous I think course we saw that if we have a conjugate prior, then it's easier to find, like solve it. So is it one of the reason? I mean, why it's difficult to actually maximize this curve?
Yeah, so one way you can maximize this is to use the gradient descent and all of that. But in gradient, so in most of the cases, you would have some restrictions on this theta. Like theta can be a covariance matrix, and so one of the restrictions is just positive. The theta the covariance matrix needs to be positive, semi-definite, and symmetric. So like you would have some such restrictions on your parameters. So in those times, the gradient doesn't perform well. I think there are some tricks that you can use, and so even gradient descent can now sometimes give you a reasonable estimate for that. So you can use like such kind of optimizations, such type of optimization algorithms to find the theta directly of log of P of X. But EM algorithm is like one of the traditional ways, and it works well. So that's why you use it. And like when there are such restrictions on theta, where so you don't need to like account for those.
Right. Okay. And is somehow anyway related to conjugate prior, or can we use any conjugate prior here?
So if you have a conjugate prior, so it makes your task easier. But here, so like so there are multiple reasons, right? So one of the reason is latent variable. So conjugate prior is like directly a MAP estimate. It does not have anything to do with latent variable models or anything. And so if you assume a conjugate prior, like then you can directly solve your map estimate. And remember, what we are doing here is not finding a map estimate. What we are doing is the maximum likelihood estimate here. So we are not accounting for some prior knowledge of theta here. And conjugate prior is a different concept that comes when you have some prior knowledge over your parameters and you want to incorporate that. So you would assume some distribution on theta, but nowhere here we have assumed some distribution on theta. Theta is just a different parameter that's free. So even here, what we are doing is just maximizing the log likelihood, and maximizing the log likelihood is just simply an MLE estimate. But now because this X is this long dimensional variable that depends on a lot of things, we have just introduced this latent variable. And so, yeah, so at the end, this entire thing is simply an MLE estimate, finding the best MLE estimate for a latent variable model. And conjugate prior is helpful when you need to account some prior knowledge of theta and making an MAP estimate, but we are not doing an MAP estimate yet. But the problems and like the problems that we face, the problems are similar. So I see where the confusion comes. Like even in the full Bayesian inference, difficulty was in getting the making the denominator extractable, and that's why we introduced conjugate prior to avoid that. And even here, the problem is similar.
So this whole entire thing, what we try to do is just the MLE estimate, right?
Yep.
Okay.
So one way to distinguish anytime is what you are doing, MLE estimate, MAP estimate. Whenever the textbook or anything mentions that you have some prior knowledge on theta, you want to ensure that theta follows this distribution, or yeah. So yeah, if any of the prior knowledge on theta is incorporated, you have some distribution on theta, then you are doing an MEP or full Bayesian inference estimate. But nowhere here we have seen that theta is just a free parameter here. So we are not assuming some distribution on theta. So if we were doing an MAP estimate, then it would be like, let's say this is a distribution on theta. Then for us, this data would be more likely than this sort of data. So it kind of, but for us, all of these theta are equally likely. So even this theta and this theta, all of these are equally likely because our assumption is theta can take any values without any distribution attached to it. So I hope this distinction makes clearer. So yeah, so in yeah, exactly this. If there was some prior distribution on theta, some values of theta are more likely than others, and that is not the case here. Theta can all the values of theta are equally likely. But by luckily, if say like as I said, these are the two things that you choose for yourself, and this comes from our modeling assumption. So like if for like how do you want to model your data? So like for GMM, this thing would have a different value, and this thing would have a different value. For PCA, these choices would be different. But say luckily you would have such choices that these two are conjugate to each other, then yeah, it makes your tasks a bit easier, where you already know the distribution of probability of, yeah, by multiplying them. If these are conjugate distribution, you already know the distribution, and then integrating that would be easier. Yeah, sorry for that. So was that clear? Did that answer your questions? Okay, perfect. So I think Jay, you were saying something.
No, I had also similar doubts. Yeah.
Okay, perfect.
But like in this case also, like we are having some sort of prior estimate, right? Basically, like based on we are basically have like q and theta, right? So we are keeping some theta here constant and trying to model for like finding out some q this which is as close to the latent space, right? So in this case also we are having some sort of like prior knowledge, right? Because we are based on like the theta value, we are kind of finding out like this q. So like
Yeah, so this EM is an iterative algorithm, right? So initially in the first iteration, this theta is not, we are not the value of theta is not, we are not incorporating it from our prior knowledge. It's just a random value. So in the first iteration, I said theta needs to be constant, and that theta is just a random initialization of theta. And now in the M step, we'll see that what it turns out to be. So but yeah, so you don't have any priors on theta. Yeah. You all the values are equally likely. It doesn't matter to you which value of theta it comes out to be. You just want to choose a value of theta that maximizes your likelihood of the data that you see, the log p of x, log p px, log of px term.
Okay.
Yeah, so I hope you are able to see my screen now. Are you able to see the screen?
Yes.
Okay, nice. So now we would move on to M step. But yeah, in the E step, just remember equate the distribution Q to the posterior. So here, what we are trying to do in the M step is did my screen froze or something? Can you see me writing anything, or is it just frozen for you? Because
it is
can you?
stuck on the EM algorithm page.
Yeah, I thought so. Wait. I'll leave the call and join again from my tab. There is some lag. Okay. Yep. Sorry about that. So yeah, now we'll move to M step, and in M step we now from the E step we have this value of distribution Q, and then now we would assume that our distribution Q is constant, and now we would yeah, we would change our theta in order to for that particular distribution. So in this diagram, why is there so much lag? I'm so sorry about this. I have no idea why there is so much lag between the tablet and so. So I think I would just avoid scrolling for now for a few minutes. So yeah, in the M step, all we need to do is maximize over theta. And now we have I other data points C are all the values that the latent variable can take in the discrete case. This is a formula for lower bound. And now maximizing over theta would yield us. So you can write this thing as QTI is equals to C minus now this entire thing is independent of theta. So you can just ignore it. So our goal becomes maximizing this. And then using Lotus, we can just simply so expectation of the slot. And like and then this the Q denotes on the distribution Q of Ti. So the value of theta is anything. So theta star, let's say, so optimal value. Then it's just and I've used capital X and T to indicate all the data points. Yeah. So and like as I said, this Q indicates that theta that your latent variable T is sampled from this. So this the distribution Q that you obtained in the previous step, on that distribution, assuming Ti comes from that distribution, you just take and this directly comes from Lotus. If you are aware of what the law of the unconscious statistician, where the expected value of this quantity is simply you can take the expected value over any distribution, and you don't need to. So it's simply expected value of f of x is simply this. Ideally, it should be p of f of x, because you change your random variable from x to f of x. But yeah, so it's like, yeah, an unconscious statistician would just replace p of f of x with p of x, and even that's fine. That works. So that's why this thing, so here instead of Q of Ti is equals to C, ideally it should be the distribution of log of joint probability of P of x and T, but Lotus allows us to directly write it in this form. So any doubts in M step? So all you need to do in the M step is just maximize over the expectations. And even this is hard sometimes. And then what people do here is use the Monte Carlo. Please let me know if it's breaking for everyone. Please give me a thumbs up if my voice is clear, my screen is clear. Okay. Cool. Nice. Sorry. Yeah. So in the M step, yeah, and finding this, optimizing over this is also sometimes hard. Yeah. Okay. So I'll repeat what I said. So in this, if you see this, so this is the equation of our lower bound, and we just open the log term, and the second term is independent of theta, so we can just safely discard it because we are maximizing on theta. And then this term, I just have compactly written as this, and so and this comes from Lotus. So if you are already familiar with it, then yeah. So all I mentioned was reiterated what is Lotus, but yeah. So it's simply what you can do is this thing. Ideally, here instead of Q of Ti, it should be some distribution of log of P of yeah. So like we know expected value of X, this integral of P of X dx, but expected value of F of X then ideally should be P of F of X times F of X dx. But Lotus allows us to replace this F of X with simply with X. So that's Lotus, and that's what we used. So this is a function of Ti, the joint probability, and we need so all we are doing is just simply this is something that you would notice a lot using Lotus to write equations compactly in all of the statistics ML, yeah, in many places. So that's all I've done. In most of the cases, you would also this is just a compact notation of this equation, nothing else.
There's a 2 sigma sign, isn't it? So what happened to the first sigma?
Yeah. So that's really so that's what I mentioned, that this X now represents the entire the complete data set. Like this sigma, so this first sigma sign I've been writing everywhere, but people generally ignore it because it's just a summation over all your individual data points I. So if anywhere, if the capital X and T are written, then it indicates all the complete data set. But yeah, otherwise there is a sigma sign everywhere. Then just replace X with Xi. So it would be over I. Yeah. Good catch. So any doubts in this? So in the M step, we need to calculate this, and in the E step we need to calculate the posterior. And this, even doing this is hard. So one approximation that people do is use the Monte Carlo approximation, where instead of calculating the expectation, theoretically it's just like now you have this distribution Q, you just sample from it, and obtain a reasonable estimate for this. And I hope you are aware of the Monte Carlo approximation. So again, I'll just write it. So if you need to calculate this, you just sample, let's say, n i's from distribution of P of X. Sum it up. So it's like exactly the definition of expectation in an I way. So this is a Monte Carlo approximation, and in this case, you would see that since P of X, joint probability of Xt is a huge multidimensional space, Monte Carlo approximation works, but it takes a lot of time to converge. So then in order to increase the convergence, there is also this Markov chain Monte Carlo method, MCMC, and using that you can make this convergence faster. But it's only like when this doing this optimization is intractable, you would use that only in those cases. And again, if we have time, it's a separate entire lecture on its own, Markov and Monte Carlo. So if we have time, we would cover it sometimes in the future. But yeah, so this at the end, again, this is the essence of this algorithm in the M step. And now after one iteration, what happens is we move closer to our estimate. So if you see, if you are able to see this diagram, yeah, here. So now after, yeah, we choose this distribution in the E step, and then now in the M step, what we are doing is moving our theta closer over this distribution to its maximum value. So the theta, now this is the maximum value, so now theta moves here. And then we have this new estimate of theta, so this becomes a theta k plus 1. And then now we would find again a lot of distributions at this new space. So now for this, we have all of this distribution, and then we would choose this distribution. So now we would have some distribution theta here. So yeah, this is getting messier, but yeah. So, and at the end, after EM algorithm terminates to get a local optimum point. So any doubts in the E step, any doubts in the M step, any doubts in the diagram, visualizing how EM algorithm works? Please let me know. And if not, I think I'll take a 1 to 2 minute break and anyone can summarize. Yeah, E step and M step for me. That would be great.
Well, I can give a go in summarizing.
Yep, thank you.
Right, okay, so what we found, we basically, so we introduced this family of lower bound, and what we're trying to do, we're trying to minimize this gap between the lower bound and the actual, the log of p of x. So we derived this equation, and which came out as this gap is nothing but just the tail divergence between the q, that's the distribution that we introduced, and the posterior, that is the probability of the latent variable given the data. So what we can explain from that is, if we're trying to maximize this whole what do you call this, evidence lower bound, then we basically minimizing the KL divergence between Q and P. So the KL divergence is minimum when KL divergence is 0, and it would be 0 when P and Q is equal. So that's what we done here. We equate Q and P, and then we solve it, and then we get our minimum KL divergence, that is the maximum of this entire evidence lower bound. And that's what we do in the E step. And then in the M step, we basically just ignore anything that's not depending on theta. So we ignore the second term, and we only focus on the first term, which is the that you wrote as a lotus form, which is the what do you call, the expected value of the log of, yeah, that's over there, he wrote the probability of x and t, and then we try to optimize that, and we keep on doing this AE and M step until we converge it.
Perfect, awesome. So yeah, so that is basically the entire thing that we did. So yeah, I hope none of you have any doubts in that, and yeah, please feel free to revisit it. If you are confused, ask me doubts anytime. Even now, just go ahead and unmute yourself or paste it in the chat. So because it's a difficult concept to grasp in the first glance. So so just to ensure that this is like all, by doing all of this after every E step, after every M step, we are ensuring the lower bound is maintained. So yeah, we just need to show that. So like after completing So initially what we started was, and this what I write in the exponent is just the iteration, like in the k plus first iteration. So this is what we started with our assumption, that this is the lower bound to log of p of x. And then in the m step, so we are kind of backtracing our step to ensure that after performing the e step, after performing the m step, that lower bound is still maintained. In the m step, what we did was this, because the in theta in the k plus first iteration is the maximum of all of these. So this thing is maintained because yeah, we chose theta k plus 1 as the maximum of all of the thetas in the previous iterations. So this is the m step, because what we are doing is an argmax. I hope that's clear. Then in the e step, what we did is equated q to the KL divergence to the posterior term, and the entire KL divergence term went to 0. So if the entire KL divergence term goes to 0, then the lower bound and the log of p of x equate to each other. So, and then, so from these three equations, we can see that from these three equations, we can see this. And then, so it's as a sanity check, you can see that with every iteration, we are increasing our, we are increasing our log of p of x. So with every iteration of theta, in the next iteration, the estimate of our log likelihood is better than our previous estimate. So yeah, congratulations, we are done with EM algorithm. We'll see a couple of examples, but that is the essence of the entire EM algorithm. So now, so in the lecture series Bayesian ML that I mentioned earlier, there is this example. I won't go over through the example, but I would encourage you all to try it on your own. And I'm just writing the example, and yeah, please give it a try at your own. So this example is easy because here, again, please remember, in latent variable models, we have these two quantities. And now this, in order to make this example easy, we would have this also as a discrete distribution. And even this is a discrete distribution. So yeah, so the example is something like x can take only 3 values, 1, 2, and 3. We want to know the distribution from which x comes from, the parameters of the distribution from which x comes from. And since it's a discrete, so let's say it's a distribution is something like 30, 0.3, 0.2, 0.5. So this is theta 1, theta 2, theta 3. We are interested in finding the theta values, which exactly say what's the probability of xi is equals to 1, xi equals to 2, and xi equals to 3. So we are interested in finding these theta I values. And now, since we need, so since EM algorithm mainly helps with latent variables, so let's say we know the data comes from a mixture of two distributions. P of 1 xi and P of 2 xi. So P of xi is equals to So this is the probability of it being sampled. This is the probability that it is sampled from the first distribution. And then this is the probability that it is sampled from the second distribution. And what are the distributions P1 and P2? This is the P1 distribution and this is the P2 distribution. As we know, xi can take only three values, 1, 2, and 3. So alpha 1 minus alpha 0, 0, 1 minus beta, and this is beta. So these are the two distributions. So it's like you toss a coin, the probability of heads is gamma, and the probability of tails is 1 minus gamma. If heads comes, then you sample from this first distribution, and this is the first distribution. And if the tail comes, then you sample from the second distribution. So given this data, you need to find the optimal value of alpha, beta, and gamma. So alpha is the parameter of the first distribution, beta is the parameter of the second distribution, and gamma is the parameter that defines from which distribution is the data sample. So, and let's say the data that you have is, there are 30 samples of first distribution, there are 20 samples of the second distribution, and there are 60 samples of the third distribution. There are 30 samples where xi is 1, there are 20 samples where xi is 2, and there are 60 samples where xi is 3. So basically this is a problem, and what you need to do is find, using EM algorithm, you need to find the optimal values of alpha, beta, and gamma. And actually it like converges directly in the first step of the EM algorithm. But yeah, so here the latent variable would be Ti for every data point 1. So like again, it's a discrete variable, the random variable, and it can take 1 or 2, either value is 1 and or 2, and 1 indicates that the data has come from this distribution P1, and 2 indicates the data has come from distribution P2. So like you can see, like this is how the latent variables are modeled. So because you made this assumption that the data has come from two different distributions P1 and P2, latent variable makes this part easier to solve it. So now the distribution would be probability of Ti is equals to 1, probability that the data comes from this first distribution is this, and the probability that it comes from second is this. So now you have this probability of, this is a distribution P of Ti. And so P1 that we saw here is probability of xi given Ti is equals to 1. And P2 that we saw above is probability of xi given Ti is equals to 2. So you have P of Ti, you have P of x given Ti. And now, yeah, so as I mentioned again, you have these two quantities. This is the problem. You need to apply EM algorithm to get the optimal value of alpha, beta, and gamma. So is the question clear? Will you be able to give it a try at your home? Should I like try to solve it further? So in each step, all you need to do is now calculate P of Ti given xi. Now, and this is like for xi is equals to 1, 2, 3. So you need to calculate like 6 quantities. Probability of Ti is equals to 1 given xi is equals to 1, 2, 3, and probability of Ti is equals to 2 again given xi is equals to 1, 2, 3. So you need to calculate all the 6 quantities, and then you would equate Q of Ti is equals to 1 with probability of Ti is equals to 1 given xi. So now you have obtained your distribution of Q. So this is the E step, and then in the M step, you would use this distribution Q to, yeah, and so this data thing, you would mainly need it in the M step, you would need it in the E step, and then you would use this data M step, and then you would maximize over the expected the equation, the expectation of log joint probability of x comma t. Yeah, the joint probability of x comma t. Yeah, you just plug find the equation of this term, just plug it in yeah, and then you would get an equation in alpha, beta, and gamma. And yeah, once you have the equation in alpha, beta, gamma, you need to differentiate it with respect to alpha, with respect to beta, with respect to gamma equated to 0. And then you would find the optimal value of theta. And in the first iteration, you would directly find the optimum values that would result in, yeah, that would result in this data set. So any doubts in the question? Would you be able, are you comfortable enough to try to solve it on your own, or should I go ahead and show you how it's done? I think it would be a good practice, if at least if you would give it a try, and then in the next session, maybe if, yeah, awesome. So yeah, I plan to start with GMM, but I think we don't have enough time for that. So so in the next session, what I'm planning to do is GMM with EM. I think that should be all. So like the other thing, and then maybe we can start with reading papers or stuff. So there is this paper on probabilistic PCA. So it's a pretty old paper, but yeah, it's and in that we can see. So that's a bit math heavy, and then that directly like ties into the last lecture, which again we had left it off abruptly, about yeah, about how to get how to obtain the operations on normals tractably without doing any of those messy integrations. So like in probabilistic PCA, P of xi given ti and P of ti both are normals, continuous normals. So everything that you would be doing is just operations on normals, operation on normals, operation on normals. And with normals, it's pretty great that you don't have to solve, you don't have to use the integrals. But yeah, the math can get pretty messy. It's not tough, it's just messy. So many variables all floating around and all of that. But like, yeah, so with all of this is just like examples of using EM algorithm to obtain the stuff that we already know in machine learning. So with EM, you can also do k-means. We'll see GMM. We saw PCA. Yeah, so all of this stuff that you have learned in ML, you can also obtain it with EM algorithm. Like, yeah, if you remember, all of this k-means and GMM both are these iterative algorithms. And that's why, yeah, intuitively, you would be able to see why EM algorithm comes into picture there as well. And I'll just maybe introduce GMM a bit, what P of xi given ti and P of ti is. So in GMM, our modeling assumption is that all the data has come from some mixture of Gaussians. And so let's say we have C Gaussians. So the P of ti is a discrete distribution. That says which Gaussian data came from. So let's say in GMM, we have 3 underlying Gaussians. Then Ti can take 1, 2, and 3 values. So the realizations of Ti are just 1, 2, 3. And this would say that, okay, probability of it coming from the first Gaussian is pi1. Probability of it coming from second Gaussian is pi2. And probability of it coming from third Gaussian is pi3. And obviously, this should hold. And the conditional distribution is obviously a normal. Yeah. So probability that, again, if there are 3 questions and C is 1, 2, 3, so there are 3 different normals. U1, so what we need is get an estimate of pi1, pi2, pi3, nu1, nu2, nu3, and sigma 1, sigma covariance matrices. So these are theta that we need to obtain in GMM algorithm, and we have this conditional distribution and the prior as in the prior on latent variables, not the parameters. And yeah, so we have the distribution on latent variables and this conditional distribution. And then, yeah, we would directly, I think, so is this clear? And are any of you saturated? Should I just stop here? Because I think I can squeeze in each step and maybe hopefully M step of the GMM algorithm. But if you are saturated and overwhelmed, then it's a good point to stop. Let me know. Okay. So if no one says me to stop, then next few seconds, then I'll continue. And I'm hoping like the silence means that you are getting all of this, because if you are not, then you are wasting your time. And I'm literally cool with explaining all of this stuff again, solving any of your doubts, repeating any of the stuff again. But yeah, please ensure that you get all of these. It might be difficult to remember, but yeah, it would be helpful to you. So, okay, then I'll continue with it. So now in the E step, as you know, we just need to get the posterior. And since it's, so just remember this P of Ti is pi1, pi2. So I'll to keep things simple, I'll just ensure that we have this 3 Gaussians. So our C is 3 here. So Ti can take 3 values, 1, 2, and 3. So we have 3 underlying Gaussians, but in a general case, it would be C underlying Gaussians. And yeah, but everything would be just same. So for each step, all we need to do is calculate this term. And as we know, with Bayes rule, this holds. And with marginalization, sorry, we can write this thing as P of xi given Ti times P of T. And we know both of these quantities, and this is just sum over all the values that Ti can take. So this is just 3. So P of xi is simply what's probability of Ti is equals to 1, it's pi1. And probability of xi given Ti is equals to 1 is the first question. So xi times nu1 sigma 1 plus pi2 times so this is the pi term. And then we already know this thing and this thing. So we directly obtained a distribution for Q. So Q is defined, Q is a distribution on Ti, and Ti is a discrete variable. So this is a discrete distribution. So Ti can take 1, 2, 3. So Q of Ti 1, 2, 3. So the first value would be pi1 times, and n as in n normal distribution. I would just do this x times u1 sigma 1 denominator, and like this denominator is p of xi, but it's so big that I'm avoiding writing it. This t is equals to this. This is pi2 times. So, and like if you see here, we know this. So when ti is equals to 1, this probability of xi given ti is equals to 1 becomes a normal distribution, and probability of ti is equals to 1 is simply a discrete value pi1. So yeah, this you obtain this distribution Q, and your each step is done. Any doubts in the each step of GMM algorithm? What we did simply is just obtain the posterior of latent variables on your data points xi. Okay, so I think no doubts here. And yeah, this is pretty straightforward. So M step is a little bit tricky, but E step is pretty much straightforward. That's it. Now you have this distribution Q of Ti. And now in the M step, what we need to do is theta. So here is a summation sign that you mentioned earlier. And this joint probability of xi ti. And now this expected value is over this term. So again, we would, similar to how we did, we would unroll it. And then this, I'm avoiding writing argmax, but yeah, this is some equation that we need to optimize for over theta. And now this again, this is the same thing. This is a compact form, and in the unrolled form, what we had seen earlier. This is assuming we just have 3 clusters. In a generic case, it would be C. And this log of, just writing the equation of normal, 2 pi. That's in a 1D case because I'm avoiding the matrix differentiation because of, yeah. So yeah, assuming it's a 1D case, then this sigma 1 is just sigma 1 square. Yeah. So this covariance matrix is simply in 1D case, a single standard deviation value. Times exponentiation of minus half. So this is a summation over all the Gaussians, and for Cth Gaussian, the mean is nu C and standard deviation is sigma C. And so like how this came is like log of Px Ti is simply log of probability of xi given Ti times probability of Ti. So xi given Ti is the Gaussian, and this is the Gaussian, this part, times pi C. This is P of Ti. And this entire thing is within the log. And then this entire thing. Yeah, it's pretty, So now we have to optimize this entire thing with respect to u1, u2, u3, similarly sigma 1, sigma 2, sigma 3, pi 1, pi 2, pi 3. So what we would do is just to 9 different differentiations, and after that equate all of that to 0, and then what we would obtain is the value of mu C, sigma C, and pi C. Okay. So obviously what I'm doing is I would do a differentiation for nu1, sigma1 and pi1, and rest of all of these would follow similarly. So differentiating equation, this is the equation, differentiating it with respect to nu1, because we are trying to find the arc maximum, so like the maximum value. So differentiating it with respect to nu1 would give us. So now you can see when C is 2 and 3, none of the terms would have nu1 in it, because this, yeah, I hope you are able to see that. Please give me a thumbs up, because if you are, so like what I'm trying to say is you would add this 3 times, and the second and third term would have nu2 and nu3 in it, and only the first term would have nu1 in it. So if I unroll this only this first term would have nu1, and then in the second and third term there would be no nu1, or yeah, no nu1 in them. The only place where nu1 can come into picture is this way, in this, and that also only in the first iteration over the summation. I hope that's pretty clear. So yeah, so we can remove this summation sign simply, because now we are dealing with only with this nu1 term, and then differentiating with respect to nu1, what we would obtain is qti is equals to 1. So because this thing is independent of nu1, and then just taking the differentiation inside the summation, then here you would have, so I'm just writing this and this together, so that's pi c times, okay, by the way, this pi and this pi are different. This pi is the constant 3.1415, and this pi is a parameter that of our discrete distribution. This pi and this pi are different. Yeah. Minus half, and then log of exponentiation is just an identity function, so we retain this thing. And then first term doesn't have any nu in it, so that goes out to 0, and then this thing is 0 minus half, and differentiating this, so this should be, sorry, nu1, this should be sigma 1. Okay, yeah, and differentiating this with respect to nu1 would just simply yield 2 times xi minus nu1 times sigma 1 times minus 1, because of this minus sign. So this becomes sigma this and this gets cancelled, this and this minus sign gets cancelled, and we are left with xi minus nu1 times, and obviously we are going to equate this entire thing with 0, because we are differentiating it and we want to find the optimal value, and at that optimal point the differentiation comes out to be 0. So this sigma 1, you can cancel it, and then what we would have is simply nu1 is equals to so nu1 times the summation is equals to summation of I is equals to, and from that you would have nu1 is equals to and this value of q of ti is equals to 1 you obtain from here, this thing, and this d is this thing. So yeah, any doubt when after differentiating it with respect to nu1, and like if if it's new 2, then this Ti, yeah, this simply would be replaced by that. So if it's 2, then this thing would be 2 and the equation, and then you would see this thing. Any doubts? I hope not. So this all thing is just simply differentiation, nothing else. And then we can also similarly differentiate with respect to sigma 1 square. And again, that's also pretty easy. This term won't go to 0. So I think I would leave that as an exercise. But so from this, you can obtain this directly, again, because when you unroll this, the inner summation, if you are differentiating it with respect to sigma 1, then only the first, when c is equals to 1, there would be a sigma 1 term in it, and hence c is equal to 2 and c is equal to 3, then this entire thing, there would be no sigma 1 terms. So all of those goes to 0. So what you would be left with is, instead of this new one here, you would have sigma 1 here. And yep, that's pretty much it. And then you just need to differentiate this inner term with respect to sigma 1 instead of new 1. This won't go to 0 because you have the sigma 1 here. But yeah, most of the stuff will cancel out. And what you would see is, instead of here xi, when dealing with sigma 1, this thing would be same, this thing would be same, but just instead of xi, it would be xi minus nu 1 the whole square. That would be the optimal value of sigma 1. And similarly, you can get the optimal value for sigma 2 and sigma 3 as well. And then now the only thing is remaining is differentiating with respect to pi I. But now what you need to ensure is pi 1 plus pi 2 plus pi 3 should be equal to 1. So how would you be able to ensure that this condition is met, as well as optimize this thing? Anyone? We saw it in the last class.
So pi is the probability distribution. So we have to make sure that that pi 1, pi 2, everything adds up to 1.
Yep.
Yeah, okay, and also I think that each of them has to be greater than equal to 0.
Yeah. So how would you be able to do this? So like, this is the equation, and you need to find the optimal value for that equation. So if there was no, if this condition didn't exist, then we can proceed similar to this thing, and we'll just do this and solve for this. But because this equation exists, then how to tackle this? This is free optimization, right? Like, we had no restrictions on nu 1 and sigma 1. They can take any values. But here pi cannot take any values. Like, pi I cannot be 1.6 something like that. Anyone? We saw it in the last class. That's a major hint. Okay. So whenever this type of constraints come into picture, what you would do is simply do constraint optimization using Lagrange multiplier, and simply, instead of optimizing this equation, we would optimize equation. So when I write EQ as in this entire messy thing, so it would be equation plus lambda times the constraint. And you would freely optimize over this instead of optimizing over the equation. And the constraint is simply sigma pi c minus 1. So it's like sigma pi c minus 1 should be 0. And yeah, this is the constraint, and you would just take this, plug it in here, so here, and do a free optimization on that. So what it turns out to be is just do a free optimize, and now you don't need to care about this constraint that summation of pi should be equal to 1, because you have incorporated that in this constraint. And with Lagrange multipliers, we saw that both of these means the same thing. And now, like this same equation, I'm just writing it over here again. Log of pi c Yep, and now what you need to do is just differentiate this with respect to pi 1, pi 2, pi 3 and equate it to 0. And then what you would observe is pi 1. I'm just skipping all these differentiations because they are pretty easy, but it's just like there are so many variables floating around. Most of this cancels out, but yeah, it's also good practice to try it on your own. And obviously, if you are not able to do it, if you face any problems, just post it on the Discord, or I can revisit it in the next lecture again. The thing after differentiating, the thing that this comes out to is this. Yep, and if it's 2, 3, then replace this with 2 and 3. So that's GMM for EM. So GMM with EM. Any doubts in this? So obviously I skipped the math in second and third derivations. It's pretty easy. There is nothing like, in the third, the trick was only to use the Lagrange multipliers and that's it. And now with this, what you would do is just, you will get 3 equations, solve for those 3 equations, 4 equations, solve for those 4 equations for pi 1, pi 2, pi 3 and lambda. And so differentiate with respect to pi 1, differentiate with respect to pi 2, differentiate with respect to pi 3, differentiate with respect to lambda. You get you all equate all of the 4 to 0. You get 4 equations with pi 1, pi 2, pi 3 and lambda is the unknowns. Solve for them. We are mainly interested in pi 1 to pi 2, pi 3, and this is what you get. So was this clear? And I think like this is a like good enough milestone if we need to stop the series here with EM algorithm and need to move to a different kind of setting. Because after this, like there are the things that I mentioned: variational inference, Markov in Monte Carlo, probabilistic PCA. So probabilistic PCA is similar to this, but it's just again, the math is much more messier than this. And when I say like messier, it's not difficult at all. It's just it's like like it's always a good idea to do messier maths on your own rather than someone else teach it to you, because when someone else is teaching it to you, then it gets by just seeing all the variables and everything floating around, it gets difficult to comprehend. But when you do it and sit it and do on your own, you would see, oh, it's nothing. It's just simple normal differentiations and integrations and all of that. So yeah, so so yeah, and like even in Bishop, there is this great chapter on probabilistic PCA. So you can also directly refer to it from there. So yeah, please let me know any comments, any feedback, any doubts, anything. I think we should be done for today. and then if with next session, if we have any other ideas, so maybe we can continue on that. Or maybe if, with once we get probabilistic programming going, what we can try to do is understand, like, all, as Deep and Jay or someone was mentioning, we can program all of these concepts and see all of this happening, and happening programmatically, how it happens in real world. Okay, I see a comment. Yeah, okay, we can do that. In Monte Carlo and variational inference. So that is an option, and other option is continue with Chalizi stats. Other option is, as Deep was mentioning, seeing how to program all of these, and visualizing all of this with programming. So, and fourth option being, we can just start with some other series, and or maybe drop this. So yeah, I think if there are no doubts, I can stop the recording. I'll give you a minute. Okay. Yep, I'm stopping the recording, and then we can talk more about it.